All right. Today we talk about again the principles of manufacturing textured yarn. So, we have seen there are a lot of methods that we have, and hopefully we should be able to actually cover whatever principles are there of manufacture. So, if we look back, what have we done? We have seen that the 4 processes like Helenka, false twist, edge crimping, turbo duo, all of them can be used to produce modified stretch yarns. And we remember that all of them give helical structures. Further also, last time we talked about that we can produce yarns with comparable stretch levels, which are generated by the modified stretch methods of the helical processes, and these are stuffer box, texturing and edge crimping. So, before we go to the bulk yarn, let us see if there are any other methods of producing yarns which are similar to modified stretch yarns. So, this is one process which is BCF. This is bulked continuous filament. It's called the BCF. So, this technology is now quite popular, and we produce crimped yarns which obviously give bulk. The name here says bulk, but actually it has stretch also. So, therefore, we said that we are not actually at the moment talking about bulk yarns, but the name of the process has been given as the bulked continuous filament yarn. And this is a very interesting process, because it is a very rapid process, simple process, and so production levels are very high. And what is the simplicity of this? For example, if you have something like a jet through which you pass the yarn, there is a perforated drum, and you obviously have a control as to how much yarn you want to send. So, a yarn which is to be processed through this process goes through this and is fed into a jet which has hot fluid. Now, fluid does not mean liquid anyway. So, it is a hot air or steam. So, when you have hot air or steam, 2 things happen. One, that you feed more, it becomes pliable, the jet is there. So, there is an aspiration. So, the yarn is actually sucked by the jet itself and then thrown onto a drum, whereby the filaments which are coming out of the jet, they strike the jet and bend, and what happens? They get crimped and stay on the drum for almost the whole circumference, and then they are withdrawn. Now, this jet is hot fluid, and therefore, it softens the yarn. then it has got a lot of velocity and therefore it throws the yarn. If it is a multi-filament yarn, not only it throws the yarn, but also it opens the filament. So, the filament bundle opens and then is sucked out, thrown out onto a drum. The main role of a drum is to ensure that the filament gets cooled before it is taken out. And so, if perforated drum means you can be having a sucking mechanism inside. So, the filaments remain on the drum connected and do not fall off, because you do not want to give any tension, because if you give tension in a hot stage, when the whole thing, the yarn is filament is hot, then whatever the crimps have been formed, they can be undone. And so, we know, let us say, particularly useful as we understand hot fluid for the thermoplastic yarn. So, polypropylene, nylon, etc., are being subjected to this particular process. So, this also produces crimped yarn, right. So, the crimps are getting generated. Interesting. Now, stuffer box also generates crimps and the BCF also generates crimps. So, they will be giving modified stretch yarn levels. So, what is the difference between the two types of products? The most important difference is, in the case of BCF, the filaments actually get separated before they are thrown onto the drum. So, if you look at a stuffer box, the crimps are formed, but all the filaments more or less bend together. You remember the stuffer box principle? So, they bend together, third, the fourth, the fifth, the sixth, all of them bend together. So, the whole multifilament yarn is bent and then you get crimps. In the stuffer box, the filaments are separated. In the BCF, the filaments are separated before they hit the drum. And so, theoretically each filament has its own crimp frequency and amplitude. The second one may have a different one, the third may actually may not follow any path, the fourth may be something else. So, what do you see? The bulk increases. So, compared to the stuffer box, the bulk of a BCF is much high, because individual filaments have been treated individually. And so, that is an interesting part of it. Therefore, the technology becomes important. The speed of stuffer box also could be very fast, but not so fast as this, because you are first softening the filaments, then you are separating them, then you are throwing them onto the drum where they get bent the way they want to get bent, there is no control, and you get really bulked filament. And this is the only technology that exists today which can be considered as a spin draw texturing process. It can be combined with spinning, right. Have you heard of spin draw yarn? Have you heard of spin draw yarn? Anyone who knows can say something about it? No. You see, normal process of making a filament yarn is that you, let us say you have melt, then you spin it, then you cool it, wind it, and then draw it. So, a drawing is a process which is separate than spinning process. All right. In a spin draw process, instead of winding the yarn after spinning, it is taken through various godet systems where the drawing is done, and at the end you get a fully drawn yarn. Okay. So, that is called a spin draw technology. For example, suppose you have this spinneret, the filaments are being spun, cooled and collected, and after this you take this whole bundle to series of godets with the differing speeds, so that as it moves from this direction to this direction to this, it keeps on getting drawn. So, you have not wound anything here, and this number would be based on how much draw ratio that you want to actually achieve. And then this yarn can be fed to the BCF unit. The one which you just saw before. So, truly you can actually combine spinning, drawing and texturing in this process. Why do we do that? Why we couldn't do this with the other technologies? It is because their speeds of texturing are close to, the best of the best would be close to 1000 meters to 1200 meters per minute. The spin draw technology, this one, all right, this technology, spin draw, operates close to 4000 meters per minute, around that time. So, how do you combine a process which is running fast to a process which runs slow? And so, you could not do that. In this case, the BCF can actually run at 4000 meters, and so you can combine. Logical but interesting. 4000 meters per minute is not a less speed, it is a very high speed. So, that was BCF. Some people, like if you are a design team, you are looking for new things to happen, you always keep looking for more new things, and so he said, well, what are you doing? We are just deforming the structure of the filament. So, crimping you have done, twisting you have done, can we do something else? They said, yeah, why not? Let us see if we make a knitted fabric, we heat set the knitted fabric and unravel it. How will the yarn look? So, can you not stretch it and that it will recover? You say, yeah, it can recover based on how much setting you have done, right. So, this is imagination, the way you try to work. The interest generated was quite large actually. Then you said, well, batch process, what is the batch process? Well, you knit fabric somewhere else, take it to an autoclave, set it, cool it and then unravel and wind. So, start from a package, go to another package, and a batch process can be done. They said, well, if you are smart enough and you think this is a good process, gives you nice structure which can be stretched and you can bring it back, can you not make it continuous? So, yeah, we can make it continuous. So, yarn is coming from certain side, one end, the fabric is getting knitted. Instead of winding the fabric, you are unraveling also simultaneously after setting and cooling. So, in a knitting system, If it is a flat bed, it works in a different way. So, a flat bed knitting machine, starting from one end, you are making a fabric, there is a heater, and then it gets cooled before you start unraveling and wind, right. So, what you see from this is that if your imagination works and your logics are fine, you can actually design any kind of a machine and any kind of process which will do approximately same job, right. And then somebody said, well, why knit at all? Why knit at all? Why can't we just simulate knitting process, that as if the yarn is going through that particular route and actually just going through, being taken through a particular route, that is it. But we do not knit because you may save energy, unnecessary knitting, yarn friction, all those kind of things. So, think of that some process called de-knit process can also give you modified stretch yarn type of yarns by simple things. You can think of many other things also, all right. So, we do not say this is the end of the game, but interesting is the people actually got so much interested, they started making machines also. That becomes interesting. An idea was not just in a classroom, beyond that. Although you may not find such processes in machines now, because others are going faster, because theoretically knitting process is not a very fast process compared to a normal texturing process. So, one always would opt, but interesting options, that is what is more important. You should get excited whenever there are interesting options available, and you can also keep thinking about what I can do to do better things. The structure, would you call it a planar structure, helical structure, or what? Planar. So, what they found is ki, well, this is not a planar structure also, because these type of structure that gets generated actually is not in a plane. The yarn moves from one, goes to the other plane, comes back, and then goes to another plane and comes back. So, you can't actually draw a plane and say, well, this loop is, you can see it is in the plane. You say, no, no, there is another plane. That means, so they said, well, the way the structure gets developed, so it is not in one single plane, because it has been said also, maybe we can give it some term like it is actually in a 3D structure, on a looped 3D structure, all right. So, that is okay. Does not harm us anyway, because if you set it properly, it will open and come back. Okay. Now, only thing is the whole multifilament yarn would behave exactly in the same way, all right. All of them will take the same shape, but that is okay. So, it will look a different type of a yarn, and the product made out of this will also look different than whatever you may have got, but that is it. If stretch and bulk, they will be definitely working around. So, in summary, if you look at it, other than the twisting process, okay, no twist here, no helical structure, no helical structure. So, stuffer box, BCF, gear, knit de-knit processes can be used. This is just to make sure that you keep remembering whatever we have talked before. Is that okay? So, now we actually come to the bulk yarn, which is the category which we have not touched till now, but we know what exactly we expect. So, what do we expect? We expect that this yarn is going to behave like this. So, remember your stretch yarns. So, this is the stress strain curve of a bulk yarn. So, it is quite different from the stretch yarn. So, it does not have stretch. The moment you extend, it starts, the stress levels keep on increasing till it breaks, depending on how you produced it. So, this is what we expect from bulk yarn. Definitely it will have large amount of bulk, you can compress it laterally, it will get compressed and hopefully recover. Those type of things will be there. So, how do we produce bulk? Well, the fiber manufacturers are also interested in doing this, and the textile technologists also interested in doing this. So, you can develop within the fiber. So, it goes into domain of the fiber manufacturers. So, they have to do something so that the bulk can be developed. When it comes to the yarn, you say, well, you give us the whatever yarn you have made, we will do the hard work to generate bulk. So, this we learnt in the beginning also, that if you change the cross sectional shape of any filament yarn, the specific volume per unit weight, per unit mass will definitely be high, and so you can say we are developing bulk. There is no stretch here you will see, but you will still be able to see that the same density of a material, same GSM of fabric will appear bulkier, just because you have introduced a different cross sectional area. The cross section area could be whatever, trilobal, pentalobal, hexalobal, octalobal, whatever you want to do, and all of them will keep changing the whole bulk process. That is the interesting part of it. Then hollow fibers, they also are bulky in that sense, their packing etc. may not give you that feel, but if you look at the dimension of material that you generate, a yarn, twisted yarn you generate, or a fabric that you make, or a filling that you do, it will again appear that the volume is large, but the weight is very less. So, in some applications the hollow fibers, there are many applications, but some interesting applications where hollow fibers have been used as a lightweight material doing exactly same thing which you want. For example, if air is inside, the thermal conductivity etc. may also get affected. Then combine both of them, hollow and profile. So, this is the domain of fiber manufacturers and not the textile technologist. Before we go further, let us say the wool as a fiber is always considered a fiber which is warmer. You never wear wool in winters, you always wear wool in winters, right, not in summer. And why do that? You see, there is some crimp, and because of the crimp which is natural, you are not able to pack the yarns and the fibers, or you are able to pack them in a lighter configuration, open configuration, so that you can compress them. So, all the woolen yarns that you may have seen somewhere, they have this characteristics. Of course, you can twist high. If you have a high twist, the bulk will reduce, but if you have appropriate twist, there will be enough bulk. But if you try to stretch this yarn, it does not stretch, it behaves exactly the way it behaves. So, one could think of wool as an interesting material because it has crimps. So, this you may have studied in your undergraduate, that in the structure it has got the main part which is called the cortex has got two types of corticular cells, which is one is called the orthocortex and the other is called the paracortex. And there is a crimp, and if you see the crimp, the orthocortex is seen and found on the convex part of the crimp, okay, and the para is found in the concave part of the crimp, wherever the crimp is, all right. So, every time somebody says that this may be just general, somebody want to know as to why this happens. So, this is what was found. So, very interesting is that when the cells absorb moisture, after all there is moisture anywhere, everywhere, and wool anyway being very hydrophilic, so it absorbs moisture in different seasons. or when you put it in water also. So, they will absorb moisture, but the interesting is they absorb moisture and then expand differently. So, the one portion which absorbs more water obviously has more pressure and wants to expand more. The one which absorbs less has less pressure and wants to absorb gets less. And so, it is something like two bimetallic strips, if you have understood them. You heat them, so one expands more, the other expands less. The one expands less goes inside, becomes the concave part of it, the one expands more. So, there is no thermal in the sense, it just says that well, absorb moisture, that also can do swelling. So, the one which swells more obviously expands more, the one which swells less. So, it is interesting is that for whatever reason, these two types of regions have different characteristics. So, a lot of studies have been done on that, and this is what happens. It is also understood by some hard work that the paracortex have more cysteine content than the ortho. Now, what that means is, so there are cross links, all right. So, the cross links, cross link means stability. Okay, we can always consider. The one which is less cross linked is more amorphous, more flexible, more ready to change the dimensions. The one which is cross linked will not change the dimensions so easily, and so you have created a difference. So, when some moisture goes in, something will happen on one side, the other thing will happen on the other side, right. So, there is a difference. So, that difference is one can lead to the formation of crimps, and like coarser fiber wool, I am talking here again. For example, the wool found in India generally has less crimps. The merino has more crimps, and that again, that these two regions are very nicely defined, they are distinct in merino wool compared to the other wool, where not only their difference may be less, but they are also randomly there, somewhere on this side, somewhere on the other side, it is not there. But in the fine wool, they are quite nicely defined, they almost say on 50%, one of them is the other 50% of the cross section, the other is there, and therefore, crimps also become more. So, that is inspiration, these days people take a lot of inspiration from the nature and then try to do exactly the same thing. So, although this is the job of fiber manufacturers, so you have something called a bicomponent fiber. So, bicomponent fiber, if you have side by side kind of thing, bicomponent fibers could be sea island structure, you could have split structures. So, it is up to you what you want to make. So, two different kind of polymers. If you do side by side, polymer A is, let us say, of one type, and the B is of a different type. Different type means, well, either because of the thermal input, they may expand differently, or because of the solvents, moisture or any other solvent, they may expand differently, and the moment they say they are going to be having this difference, then you will see crimps generated. So, if you have the crimps generated, so principle is very clear, you got to have two different polymers, side by side is the best way to do it, and then you get crimps. So, principle is clear, like a bimetallic strip, which is used, generally used for what? Bimetallic strip. Is it useful or is just a principle and thank you very much? Does it have any use anywhere? Right. So, they are sensors, they can be used as sensors. So, whenever there is a heat generated, you will see they are behaving differently and you can sense something happen. So, the same principle in a bicomponent fiber, if you use, then theoretically what kind of a structure we are likely to get? What kind of structure we are likely to get? If suppose this was, these two polymers had different coefficient of thermal coefficient of expansion, what kind of structure we are likely to get? Yeah? Very good. So, you can get helical structure by bicomponent fibers by choosing suitable polymers with different properties. So, it does not have to be thermally different, it could be swelling capacity could be different, for various reasons you can always get to this type of thing. So, you may say, well, this is a helical structure, this will be a stretch yarn, why are we actually working on a, under the bulk yarn category? So, it so happened that people were not able to get the kind of helix and the number of helices per unit length were not so high for it to be considered so nice that it is going to replace a stretch yarn, right. But they would cut into staple and then use them, and they say, oh, this looks like a crimp. So, one fiber, the other fiber, and so on and so forth. So, they made the yarn. So, one of the interesting product which we had, the acrylic bicomponent spun yarn system, where you would say it is a bulky yarn, right. But if you are very, very smart and the difference between the swelling capacity are so large between A and B, that they actually make a beautiful helix, which you can see that when you say it is there. You see the helical structure, it is not there, it is here, a little bit of a difference. Okay. So, you cut them into staple fibers and then mix them and use to make a yarn out of it, like a wool. You say the inspiration from wool. Wool is also a staple fiber. So, you make staple yarn, you say this is just like wool, we cut it out and then make a staple yarn out of it. Any problems? There is no problem. Go ahead, do it. The next thing is that we get something from the fiber manufacturers, and then we say, well, now we are developing bulk in the yarn. So, three interesting techniques have been used. They are air jet texturing, where you have filament yarn, work on a compressed air jet, and you get something which is interesting enough to produce a textured yarn, which is in the category of bulk yarns. Then high bulk yarns, which have again a staple fiber, based on staple fiber. The air jet texturing is a filament, right, generally filament, but not necessarily. High bulk yarns we talk about, they are basically staple yarns made from staple fibers. So, and the other is called a biconstituent yarn. There are two fibers. In high bulk there may be same fiber with different properties, and biconstitute could be two different fibers with different properties. So, let us take the air jet texturing, like the false twist texturing. This is also one of the very popular techniques, right, and so commercially a success. So, what do we do? So, there is something called a black box, all right, which is called a jet, where the compressed air is being fed. Once this is there and you feed your yarn, it goes into the jet, and from the black box, when it comes out, it gets textured. So, how this kind of a thing comes? The loops, various kinds of loops are generated. How does it happen? Details we will learn later, but one interesting thing is, between these two sets of rollers, you give overfeed. So, you give overfeed between these two sets of rollers, so that you have enough length of the filament between this zone where a lot of entanglements would take place, and then you get entangled yarn. If you do not have any overfeed, the filaments will not be able to move from one side to another side, they will not be able to make a loop, bend or whatever. So, you give overfeed, and good amount of overfeed, 20%, 40%. That means the length of the whole thing will reduce by 40% if you give 40% overfeed. But then you want bulk to be developed. So, you want more bulk, more loops have to be formed, more entanglements have to be formed, and therefore, you give overfeed. That is a controlling factor. Other controlling factor of course, will be the pressure of the compressed air, and the most important controlling factor is the jet itself, the design of a jet. So, it is not that anything that you feed and everything will come out nice, something interesting has to be done. But the most important thing is called a mechanical process, mechanical, you know. So, you do not have to worry about the chemical structure, because you are saying in the other thing there has to be something called a heater, then heating, then cooling and setting. It does not matter, it is just an entanglement process. If it is entanglement process, viscose can be processed, acetate can be processed, polyester can be processed, nylon can be processed, it does not matter. So, the basic fundamental process does not require any chemistry, not concerned. We do everything mechanically, handle, optimize mechanically and get a nice yarn at the end of the day. The thing which it actually attracted quite a lot of interest, that any fiber can be thrown into it, something will come out. Thermoplastic, non-thermoplastic, no problem. Circular cross section, profile cross section, hollow, it does not matter. Whatever you want to throw in, something will happen. So, what you have to bother, that is an optimization process. Then you can actually generate blends, throw viscose and polyester together, something will come out which is entangled, not separable, you cannot separate them very easily, otherwise not a good yarn. So, you made blends. Think of how do you make blends, what difficult process, fiber coming from here, fiber coming from here, mixed in a certain blend, keep doing all kinds of cardings and all operations, and then you get some yarn. You say, throw filament from one side, the other filament from the other side, you will at the end you will get a blend. You will say what else? So, we can make a core sheath structure. That means one yarn is actually in the core, the other is forming a sheath. And how do that? You just control your overfeed. The one you want on a sheath, give more overfeed. The one you want in the core, give less overfeed, and you get a different yarn. And if they are colored also differently, you will see something else. For example, you may be interested polypropylene in the core, viscose on the surface, possible. Strength coming from somewhere else, bulk coming from somewhere else, beautiful structure. Fancy yarns, all kinds of fancy yarns can be made. That means there is a lot of advantage. That is why you have interest in such technologies. Simple, but works more. A complex technology which may cost more can also work if the product is so much in need. If you just find, well, the purpose to be served is only this, then why make the technology very complicated? If you make it complicated, of course, you will pay more and the product also will cost more. This is one interesting technology. Everything is not hanky dory, we will learn about it later. So, what kind of a structure? Well, each filament may actually keep making loops, the second one may make loops, may make more loops, may cross over, bend and go, the third one may do something else which you may love or not, does not really matter, the guy is going to behave the way it has to behave, and suddenly if it entanglement is good, you see what is the dimension of so called yarn versus what is the dimension of the bulk yarn. So, it depends on what you do and how much you do, the bulk will get. But here also entanglements are so nice, very nice, that you do not have any stretch. In fact, if you stretch this yarn and it extends, it will actually not come back, it will remain in extended form, because all this is by friction, interfiber friction. And once you have applied something and because of some slippage it has gone to a different position, and because of friction, why will it come back? There is no reason for the filaments to come back. So, they can change shape, that is the challenge. So, in the high bulk category, the most popular product is high bulk acrylic yarns, high bulk acrylic yarns. In fact, when the acrylic fibers came and this is the kind of product which came in, it just replaced wool. It gives you same feel, again staple fiber yarn, it just replaced wool. Today you go anywhere in the market and say I want a woolen yarn, 99% chances they will give you an acrylic, and you will be happy because it looks very nice and exactly same. It works on the principle called the differential shrinkage again. You remember we said in the case of bicomponent yarn also, it is a difference between the two types of things. So, here you can make one fiber, let us say acrylic fiber, which has let us say shrinkage on heating, let us say, thermal shrinkage. One yarn, let us say yarn A has close to 0% shrinkage, and yarn B or a fiber B, let us say fiber B is close to 30%. This is called difference. That means you heat one fiber, approximately its dimension will be remain same after heating. Other fiber, its dimension will reduce. And what do? You mix them up and let us say 50% make a staple yarn, and then subject it to thermal treatment. If you subject it to thermal treatment, what will happen? The one which is the fiber B is called a shrinkable component. It will shrink. Let us say fiber B, it has length this, after heat treatment the length is this. Then the other one is a more important candidate called the non-shrinkable. So, it cannot shrink. So, what will you do in a compact situation in which every fiber is entangled? So, it will crimp, it will bend, it will make loops to accommodate itself. So, it cannot say independently that I remain as long as I was before. So, theoretically yes, the length of the fiber will remain the same. B has actually shrunk, thermal shrinkage. In the other case there is no shrinkage. So, either it has a possibility to remain at the same level, so length remains same, but others around the thing are contracting. So, it has to bend and then get in. And if your twist levels have been optimized in a nice manner, you will suddenly find the bulk of the yarn is increasing. So, differential shrinkage principle, interesting, and this is commercial. So, this principle is commercially successful, products are there, there is a bulk yarn. And what interesting thing is that only acrylic high bulk yarns are available in the market. You do not say I want acrylic high bulk polyester yarn, you see they are not there. It is also very lucky that you actually had something called acrylic. The same thing does not happen with polyester, that you can make acrylic fiber, one which shrinks up to 30% or more, other can be stabilized. So, here there was a concept which we can say that you can freeze amorphous orientation. Freeze, what do you mean by that? Normally what do you do? I draw, take it to the heat setting and expect the heat setting would help me to develop crystalline regions and the fiber will not shrink. That is what I normally want, that my things must not shrink. And by heating some of these material like polyester, polypropylene, nylon, they immediately start crystallizing, and so system becomes stable. Very interesting in acrylic that actually you can go through a certain temperature system, extend it, it does not crystallize very nicely, but it can make large number of polar bonds, which is because of the nitrile group. There are so many nitrile groups there and they can make polar bonds, and so when you stretch, so new polar bonds have been created because of the so many nitrile groups, and you leave it there, it does not want to come because of this, but it is still not crystallized. So, this thing is not possible in other fibers, they immediately crystallize. That is, you can actually freeze amorphous orientation. You see, anything which has been oriented has a tendency to shrink. The one which is not oriented does not shrink so much, right. So, oriented structures, polymeric structures would have a tendency to shrink. So, that is what you are doing, stretch it. So, you have given a potential that will shrink, but if it crystallizes it cannot shrink. In this case, you can actually freeze amorphous orientation, and so you can actually create fibers which are only oriented without crystalline. Others you actually go to more thermal conditions where some crystallization will take place, stability will be there, and 0% shrinkage is never there, maybe 1 to 2% shrinkage, and so there is a difference is quite large, and then you get what you call as acrylic high bulk yarn. All right. So, the other one is biconstituent, means that you have two different fibers. If they have differential shrinkage, you can get it. So, people have used various type of things, blend of acrylic and polypropylene, acrylic shrinkable fiber, polypropylene non-shrinkable fiber. People have said, well, I make jute and wool mix and I give some chemical treatment so that one of them shrinks, the other does not shrink, so you suddenly get bulk, right. So, this is how people have been working around to use different kind of thing using the same principle and get bulk yarns. So, we take 1 or 2 minutes and say beyond the classification, right. So, there is no, whatever classification we have done, stretch yarn, modified stretch yarns, bulk yarn, this is beyond that, you can still get bulky fabric. The bulk can be developed and stretch can be developed in the fabric itself, you know. For example, the crepe bandage, you see the crepe bandage is a fabric, nothing is being done at the yarn level to give the stretch. What you are doing is very high twisted yarn have been woven in a light GSM kind of environment, and whenever they get a chance, they, because of their energy reduction, you want to go to a stable state. So, the crimped yarn or the twisted yarns want to come back. So, one can make crepe-on fabrics is one of the things where one set of yarn has got one twist, the other set have got another twist, and you get beautiful effects, bulky effects can be done. Other is interlacement, which is not a bulk development, but it has some motivations, some inspiration from whatever is happening in the bulk yarn, but part of the filament industry and part of texturing industry. Interlacements can happen. So, we come to the end of this today, that various methods which can be used to produce textured yarn, we have learned, whether it is a stretch yarn or a modified stretch yarn or bulk yarn. The principles involved in producing such yarns are also very widely different. The structure that is produced, generated also is very different, could be helical, planar, 3D, entangled structure and so on and so forth. All right. So, in summary, what we have learned is there are the large number of methods that can be used, and some of them have become commercially success. So, as we move further, we will talk more about the commercially successful technologies, and we will keep appreciating the principles people have generated time to time. Thank you. All the best.